Am I loud and clear? Is that okay?
Yes, yes.
Thank you. Thank you.
Yes.
Yes, Sudhara, you are.
Thank you. So, I think our friends are coming right now. So, we'll wait for some other time, some more time. Okay. I hope you remember I've introduced myself in the very first class with Professor Anna. And I am Sudhakar, and I'm a postdoctoral researcher. And I've done my graduation and post graduation in aeronautical engineering, aerospace engineering. And I did my doctorate, PhD in aerospace materials in India. And beyond that, currently I'm working in biomaterials. So basically, I work in extension of the materials life, like fatigue life. So fatigue is my research area actually. So fortunately, I'm going to share some of my experience today in fatigue topic in your class. Okay. Okay. Okay, see, my class is, I want to be an interactive class. I don't want to keep on talking about the facts, about the topic, definitions. I don't want to do that. It is, it's widely welcome if you can talk with me, if you can answer me, if I'm raising any questions. Okay, that'll be fine. Just give me a moment. Let me share the screen. So can you see the slides?
Yes.
Yeah.
Okay.
Yeah.
Just give me a moment. Just give me a moment. Actually, a lot of instructions are coming in Portuguese. Uh, it's a little tricky for me. Yeah. So can you see the full screen? No?
Yes.
Okay, thank you. So yes, today I'm going to talk about metal fatigue. So I hope you all would have come across the term called fatigue in your daily life, right? So fatigue, what simply if I want to say, I can't talk, at this pace for another 1 hour, that's no problem for me. Okay, yes, I can talk. And if this class extends for another 1 day, definitely I cannot talk, even at my pace, even at the loudness which I cannot talk for a long period. That's all. That's called fatigue. Okay. So a metal will fail even under its yield strength over a period of time. That means a time delayed failure. Okay. That is a short introduction about a metal fatigue. Let me, you can see some photographs in the slide. So in that photograph, you can see the daily day you would have come across the cycle pedals and many hacksaw blade and some exercising equipment. Everything would have failed over a period of time suddenly without any warning you would have come across in your life. All these failures are attributed to the fatigue of metal. Okay, so right from the normal pedal, it the failure extends up to a huge aircraft failures like 520 valuable human lives lost in 1985 Japan airline crash. So that much important it is. Okay, so it is a catastrophic failure which caused that entire aircraft to get vanished. So it's about 520 lives we lost. So this is a small introduction about the fatigue, and it's a part of your syllabus. Okay, so it's a part of your syllabus, that too a very smaller portion. So I won't go more deeper. I'll have a very cursory overview of fatigue. Okay, so introduction. So as I said before, the term fatigue is appropriate to mention because it refers to a time-delayed fracture of materials subjected to cyclic stresses, below that causing the plastic yielding or tensile failures. That is very important, okay? Because usually engineers will consider a material based on their yield strength. Just give me a moment. I think some of the friends are joining. Give me a moment. Okay. So fatigue is a natural consequence of the inherently stochastic loading condition of structures and components. So inherently stochastic loading, that means a random loading and continuous loading. Okay. So that is a natural consequence. Obviously, it's a natural consequence. We are not purposely we are not making it to happen, or it is happening naturally. Okay. So the term fatigue is borrowed from the human reaction of tiredness due to the repetitive work. That's what I explained in the very first slide. Okay. So the tiredness, when the humans get tired, the metal get fatigued. Okay. That's all. As simple as it is. So in addition to the cyclic loading, stress concentration, that means a geometrical feature of the material, and corrosion, temperature, and residual stresses can initiate the fatigue failure, not only the cyclic loading. Along with this happenings, along with these futures, the fatigue will be initiated, even the fatigue will be accelerated. Okay. So let me come to a very important topic, the importance of fatigue, because why we need to learn. So what makes fatigue so unique compared to the other type of failures? So mechanical failures due to fatigue have been the subject of engineering efforts for more than 150 years. More than 150 years, the people are dealing with the fatigue failures, and they are working on quantifying it, or they are working on analyzing it. So right from 1850, if I'm not wrong, in 1850, the first person who analyzed the fatigue and reported a test method for fatigue analysis is Euler. He is a German railway engineer, and there is a topic in your syllabus called Euler curve. It is named after him. That is the first way to represent the fatigue result of a material. Okay, that is a proposed method. So almost 50 to 90% of entire mechanical failures is due to fatigue. Just imagine 50 to 90% of entire failure. Whenever, whatever the material fails, that could be the fatigue could be the reason. That's exactly what we have to think. Okay. So annual cost is related to fatigue of materials in the US economy is 3% of the GNP. 3%. That's a huge percentage. Okay, so fatigue is the most common failure in all field of engineering. It is not only to the aerospace engineer, it is not only to the mechanical engineer, it is to automobile engineer. Even in electrical engineering also there is a fatigue failure, even in electronics engineering also, everywhere fatigue is everywhere. Okay, fatigue failure is particularly insidious because it occurs without any obvious warning. That is very, very dangerous and important thing to note, because the component or the part will be working as usual. Today it will be working, but tomorrow suddenly it will fail. Till yesterday it will be working, but today it will fail without any warning, just like that. So what will happen if that failure happens in the mid-air? The entire aircraft will crash. Okay. What happens when you are going in 120 kilometers speed in your car, axle get failed? Then there will be a huge disaster will happen. Okay. So fatigue has to be addressed properly. Before addressing it properly, you need to understand it properly. Okay. So these are all the examples around you where which will be failing due to fatigue. First thing is door springs. Okay. The second, the simple components. Let's see the simple component. Definitely, these components will be around you when you are listening to this class. Okay. Door springs, tennis rackets, electric bulbs. Electric bulbs, yes. If there is a fluctuation of electric current, or else when you are keep on switching it on and off over a period of time, it will get fused one particular. Okay, one fine day it will just go off. Okay, that is also because of fatigue. Paper clips, that's a very common example. If you can see a lot of videos in the YouTube, they will be explaining fatigue right from the paper clip. So just paper clip, if you just move it up and down, close it and open it and close it again and again, the clip will fail. Okay, so these are all the common components which you are seeing in the day-to-day life, and some complex components also experiencing the fatigue failure. They are ground vehicles, ships, aircraft, and biomedical implants. Yes, the knee implants and other things will get failed over a period of time. Okay, so that is very insidious, because once the implant get failed, the resurgery is totally a painful process for the patient. Okay, so we have to design, we have to create bio implants which has a good fatigue resistance. Okay, and other thing is automobile steering linkage, engine connecting rod, ship propeller shafts, pressurized airplane fuselage. That is very important. You know, the very first jetliner which experienced the failure is because of this pressurized fuselage. The very first jetliner is Comet aircraft. Okay, so that Comet aircraft, the first time they went to 24,000 feet above the Earth, like sea level. So during that time, the entire cabin has to be pressurized. Okay, so when the entire cabin has to be pressurized, the entire circumference of the cabin is experiencing the load, that to a fluctuating load. When it is taxiing, one load will be there. When it is rising, one load will be there. So because of all these things, and accompanied with the stress concentration due to a window, the failure happened. That is the first disaster happened in aerospace engineering. Not in aerospace, or cannot say in that way. Maybe a jetliner disaster. Okay, the first jetliner disaster. That is a common disaster. You can go ahead, search in Google, and you can learn about it. It's very interesting. Okay, so pressurized airplane fuselage, landing gear, hip replacement prosthesis, everything. Just give me a moment. Is anyone is waiting outside? Because if I go, again I have to come back here. There's some glitch. Yeah. Guys, am I clear? Is that everything fine? Friends? Is that everything fine?
Yes.
Yes, up to now, yes.
Okay, to the bend, right? To the bend. Thank you. So you can see the full screen, right?
Yes.
Okay. Okay, let's go to right now. What you have learned, what I have discussed is we have started with what is fatigue and the basic definition of fatigue, and then what is the importance of fatigue and where you can see the fatigue failure, everything we have seen. Okay, let's go much deeper. So, what are all the steps involved in fatigue? That is, we have to see. We are going to see it right now. So, first thing is crack nucleation. Immediately the fatigue failure is caused due to the crack. Okay, so if there is a crack, then there should be a nucleation. So first one is crack nucleation, second step is crack growth, and the third step is crack coalescence. Okay, so crack coalescence, maybe crack nucleation is nothing but initiation, growth is it's growing, coalescence could be tricky, coalescence is nothing but combining together and the final fracture. Okay, so let me tell you in deeper way, the nucleation event is the least understood various aspect of fatigue. Just imagine that's the least understood because there are various theories evolving and existing in nucleation of crack. And so in all materials, so we in a very conventional strength of materials, you would have seen. Just give me a moment. Someone is outside. Okay. Yeah. So, in all material, in a conventional strength of material, we used to say the material is homogeneous and there is no flaw in the material. So that's how the conventional engineering principles have been developed. But that is not so, obviously. Okay, in all materials there will be an inherent flaw. In all materials there will be a stress risers. So these are all the these are all said to be the important. Reason for the fatigue crack initiation. In all materials, there are regions of local inhomogeneity that result in local softening or surface flaw that cause a local stress concentration. That is very important. Okay, the local stress concentration. In the inhomogeneous plastic flow occurring at a microscopical level, such flow can take place even when structure is elastically stressed. Even in the elastical, you can think that I am stressing the material well below the elastic limit. But what exactly happening if the material is having an inhomogeneity or a crack or some third particle in the microstructure? So what will happen at that area? The stress will get enormously increased. So that is called stress concentration. Okay, so that stress will lead to a local plastic flow. Okay, so the surface, then if you just consider like a slip bands which is arranged in a crystal. Okay, so when the material is subjected to a cyclic load, that some slip bands will be stuck inside, some will come out. So it will create an intrusion and extrusion in the crystal surface. Okay, this intrusion and extrusion over a period of time, that will create that will remain there, that will be a persistent over there, and that will create a crack initiation site. Okay, that is embryonic for the crack initiation, fatigue crack. So from there only the crack will get initiated. Okay, so this surface protrusions are the origin of persistent slip bands. Okay, I hope you would have come across a system called PSBs. Okay, persistent slip bands. Do you have any doubt in this, guys? Because this is tricky. It's fine. Yeah,
Yes, it's fine. It's fine.
fine. Okay, to the pen. Okay, thank you. See, please stop me then and there. Don't hesitate. No problem at all. Because I need you all to understand what I'm teaching. Nothing else is required. Okay, so let's go for the crack growth. So what is happening in crack growth? We divide the crack growth in two stages. One is, just give me a moment, another person is coming. Yeah. We divide the crack growth in two stages. One is stage one crack, so formed and propagation in the direction dictated by the plasticity. The stage one crack is need not to be normal to the applied stress. Okay. I hope you would have imagined when a load is applied in one direction, the crack will grow in the perpendicular direction to the applied load or a normal direction in the applied load. But due to in the stage one will not obey that imagination. Okay, the stage one will be the direction of the crack growth will be dictated by the plasticity of the material. The stage two will be normal to the direction where the load is applied. When it reaches to the certain size, the stage two crack develops from it, and this crack propagates at a rate defined principally by the applied stress range and so thus in the direction normal to the principal tensile axis.
Dr. Hajan,
Yep.
could you turn on your, or somehow apply your mouse, make it visible or laser point so we can see where you're pointing on the picture on your presentation,
Okay,
please?
okay. Yeah, can you see this? Can you see this now?
I can't.
No, I am just using a laser pointer right now. Can you see that pointer?
No, the laser no.
I can't. I cannot.
Okay, let's see. Stop share. So you can see the full screen, right? Step by step animation you can see. Can you see that?
The screen is okay. Your presentation, I think everybody can see. What we cannot follow is your mouse or pointer or laser. It's not showing on the screen, so it's not so easy to
Okay, I understand.
follow what you
understand.
say in the picture and the picture on the slide. So it'll be easy if you.
Yeah, I understand. Thanks for sharing. Let me try.
I think we can see the full screen.
I can see the full screen, but I am
Mouse
in
of the
my
laser.
end. In my end, I can see the mouse, but I don't know why you cannot see that. Can you see that? I'm drawing in the screen.
No. Maybe if you go to, I don't know if you're using the presentation mode, you are in the edit mode. So if you change to presentation mode, I don't know, just.
Let me try. No, really sorry about it. I couldn't make it up. you. Sorry, let me try to.
Yeah, go ahead.
Yeah,
Let's move on.
really sorry about it.
Don't worry. Don't worry.
Yeah. The problem is I'm getting a lot of instructions from Google, but it's all in Portuguese. I cannot, I couldn't translate it. That's a problem. That's okay. I'll try to do it. So you can see it right now?
Yeah, we can see the presentation.
Yeah, step by step, you can see it, step by step.
Yeah.
Yeah, like one by one only it is coming, right?
Yeah.
Yeah. Okay. So you can see a Roman letter 1 near the surface. Am I right? In the diagram, can you see that? Okay.
You are on page 7 or page 8.
I'm the page number crack growth.
Yeah, okay, this is it.
Yeah, in the crack growth, you can see a diagram. Can you see that?
Yes.
Yeah, in that diagram, can you see 1 and 2? 1 is near the surface and 2 is little away the surface.
Yeah, that's correct.
Okay, that 1 is the stage 1 crack growth. Okay, so that is not normal to the applied load. Am I right? That is not perpendicular to the applied load. It is somewhat inclined. So the direction of the crack growth 1 is dictated by the plasticity of the material. Okay, that's what I'm trying to say. And stage 2, it will become normal to the applied load. Stage 2 is, you can see in the diagram, the 2. Can you see that?
Yep.
Yeah, that's what I'm trying to say. Let me take some time and explain you. Don't please don't hesitate. Please stop me and ask me if you have any hesitations. Okay, thank you. So fatigue cracks nucleated and grow as a result of cyclic stress. Obviously, that's what we were discussing from the slide 1. So that this is not one by one cycle, it won't happen. By repeated cycle only, this fatigue crack growth stage 1, stage 2, everything will happen. Okay. So during the slow growth process, the crack advance rate relates to the frequency of the stress or strain cycle. So how advanced the crack should go, that should be determined by the frequency of the stress cycle. Okay. So crack coalescence or final fracture, that is the final stage of the entire fatigue process. Okay. The slow crack growth is interrupted by final fast fracture resulting from the inability of the cross-sectional area. So what exactly happening? Can you imagine what is happening? So the crack initiated in the surface, that is traveling to the core of the material. So once a critical length the crack reaches, what happened? The material circles, the cross-section area is not big enough to take up the load. Obviously, the cross-sectional area will get reduced because partially it is separated. Am I right? Can you imagine it? What I'm telling?
Yes, yes.
Yep.
Okay, so immediately the material get failed. So because the cross-sectional area is not big enough to respond positively to the applied stress. That's what the final fracture is. Okay, this is how the fatigue crack initiate, grow, and final fracture happen. Okay, this is what the entire process is. Okay, let's come to important parameters of the fatigue. Why these parameters are developed, why the yield strength is developed, why the tensile strength is developed, in order to mention the material property, in order to analyze it. Okay, for that only it has been developed. Similarly, in fatigue, there are some properties, there are some parameters which are developed in order to quantify the fatigue behavior of the material. Okay, so the very important thing, first thing is maximum stress, minimum stress. Okay, so sigma max and sigma minimum, that is two things is very important. How far you go in tensile, need not to be in tensile stream. How far you go in the positive stress, it is positive maximum stress. How far you go need not to be in negative. How far you go, the lowest stress you are in algebraic stress you experience in the cycle is minimum stress. Okay, so that is sigma max and sigma minimum. What is sigma mean? About which the sigma max and sigma minimum is acting on. About which, if I want to say in a simple English. Okay, so sigma mean is nothing but sigma max plus sigma minimum divided by 2. So about this stress only the fluctuating stress are happening. Okay, the stress range, the entire range, that means the entire thing, sigma max to sigma minimum, what it is there. So sigma max minus sigma minimum, that is the entire range. So sigma r is nothing but sigma max minus sigma minimum. Then amplitude stress. So what is amplitude stress? Sigma, the entire range divided by 2. Sigma r divided by 2. Okay, so that is called the amplitude stress. So and then very important parameter is r. R is nothing but the stress ratio, sigma minimum divided by sigma maximum. If you go for a fatigue analysis, if you do an experimentation, these are all the parameters you need to be knowing without any confusions. Okay, you need to be very clear in these parameters so that only you can handle the machine properly and can get the results out of it. Okay, so this how the entire, because the sinusoidal curve is nothing but the loading curve. Okay, so as I said before, it is a cyclic stress, cyclic loading. So there'll be up stress and there'll be down stress. Okay, if I continuously do that, then I'll get a sinusoidal curve. Are you okay? To the bit?
Up to now, yes. Yeah.
Okay. Okay. So this is type of fatigue cycles. Okay, there's another important topic which we want to discuss. So this type of fatigue cycles is, first thing is fully reversed cycle. What is fully reversed? If I go certain MPa in tension, the same amount of stress I have to go in compression. Okay, that means sigma max is equal to sigma minimum, or not exactly in numerical value it is equal to, but it will be in opposite sign. Sigma max is equal to minus sigma minimum. Okay, so sigma max and the load fluctuates between sigma max and sigma minimum amplitude. It's also symmetric about. So if obviously if you apply this thing in the formula which we discussed in the previous slide, then the mean stress will be 0. Am I right? So if the mean stress is 0 and sigma max is equal to minus sigma minimum, then the cycle is called as fully reversed cycle. This is a first cycle which is developed by Aula for quantifying the fatigue behavior of the material. Okay.
I don't know about the other, but my screen is still on slide number 7.
Okay. So you cannot see the types of fatigue cycles?
Now you change it. Now it's slide number 9. Yeah.
Oh, you can see that. Okay. Okay. So everyone can see the slide, which is type of fatigue cycles.
Yes, but it's not on the full screen.
It is not in the full screen? Okay.
No.
Now? To the Ben? Can you see it now?
Again, we can see the PowerPoint presentation, but you are in the edit mode. You're not in the presentation mode. I think this is one of the reasons that we cannot see your screen or your mouse or your pointer, laser pointer. It's because you are always in the edit mode. You don't change to the presentation.
Yeah, I understand. But in my end, I am in the presentation mode. I'm
That's
not in
okay.
the I
I don't
don't
know
know
what's
anything.
happening.
Yeah, exactly.
Maybe you're sharing the wrong screen. I don't know.
Okay, maybe. Yeah. Let me check that.
Are you sharing the screen or
The work area.
Yeah.
Okay. I'm sharing the work area. One window. I'm sharing one window. Um, can you see
Now
me?
it's on full
This
screen.
is it. Now you got it.
Now,
Now you're sharing the right screen.
Yeah.
Yeah. Yes.
yeah.
Yeah. Thanks a lot for helping me. Actually, I handle classes in some other platform, Zoom, Microsoft. First time I'm handling in Google. Thank you. So you can see the pointer also right now. Can you just
Yes, we can see everything now.
Yes.
Now it's perfect.
okay.
Yeah, laser pointer. Yeah, that's okay.
Okay, thank you. So this is fully reversed. So the load fluctuates from sigma max to sigma minimum, and the amplitude is also symmetric about the zero mean stress. Okay, so that is fully reversed. Repeated cycle is nothing but sigma max and sigma minimum are asymmetrically related to the sigma zero stress level. Zero mean stress exactly. I just missed that. Mean word over there, I guess. Okay, so it is not symmetrically positioned with the mean stress level. That means zero mean stress level. That is repeated stress cycle. The last one is a random cycle. That's what exactly happening all around the world. So there is no constant amplitude. There is no zero mean stress level. So the stresses are happening just like that, up and down, up and down. Okay. There is no proper way to quantify it. Is it fine?
Yeah.
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 So let's come to the Euler curve right now. It's a curve de Euler, right? Yeah. So in this Euler curve, let me tell you point by point what he quantified and what he presented, everything. Then we'll see the example for the Euler curve. Okay. So in 1850, a German engineer, August Euler, developed a methodology to test the fatigue and represent the results. That is, the engineering fatigue data is usually plotted as a SN curve. That S stands for stress and N stands for the number of cycles. Okay, the x-axis is plotted as log n. Why we go for a logarithmic scale is obviously because we work in million and million of cycles. Okay, so for example, 5 million of cycle or 7 million of cycle is considered to be a run out of sample. Just imagine. So I cannot go ahead and put 100, 200, 300. So they use the logarithmic scale for the plotting the n number of cycles. Stress plotted could be one of the following sigma A or sigma max. That means they may plot against stress amplitude stress or a maximum stress. And for each plot, the sigma mean and the stress ratio will be constant. There won't be any change. Sigma mean will be a constant one and the stress ratio will be a constant one for each and every set of data, for each and every set of SN curve. Okay, for each and every SN curve, not set of SN curve. Okay, typically the stress value chosen for this test is lower than the sigma y, obviously, because if we go beyond the sigma y, they will initiate the plastic deformation in a gross way. As a whole, you will initiate the plastic deformation. So there's no sense in doing the fatigue testing. Okay, so that means high cycle fatigue testing. So always we will start with the stress level which is lower than the yield strength, and hence the SN curve deals with fatigue failure at a larger number of cycles. So these are called, which is more than 10 power 5 cycles, then it is called high cycle fatigue testing. Okay. And it is to be noted that a nominal stress of which is lesser than sigma y, but microscopically, that's what we were discussing before. You might be like subjecting the material to the stress which is far below the yield strength, but locally, microscopically, there will be a plasticity happening, and which leads to the accumulation of damage. Okay, so starting with the stress of 2/3 of the static tensile strength of the material, the stress is lower till the specimen do not fail in about 10⁻⁷ cycles. We usually used to take 10⁻⁷ cycles. So if it is so, the material is said to be fine. So there is no failure up to 10⁻⁷ cycle, then that particular stress amplitude is considered to be a fatigue limit of the material. Okay. So the low cycle fatigue is totally different. If the testing is done between 10⁻⁴ to 10⁻⁵ cycle or lesser than 10⁻⁴ cycle, then that testing is called low cycle fatigue testing. In this, we don't take a stress range which is below than the say yield strength. We may take little higher than yield strength. That means you can initiate the plastic flow. That's no problem in that particular low cycle fatigue testing. The entire the testing, reporting, everything will differ for this. Okay, and we don't go into it as of this class is concerned. Okay, so let's go to the endurance limit. That's what the key feature we need to know when you analyze the fatigue. Okay, that means a stress below which the material is said to be endurance, said to have an endurance to the fatigue failure. That means below which the material will have a n number of cycles. That's what is called endurance limit. Let me tell in a proper way. The coordinates here, sigma A and NF is logarithmic scale. That's what I explained before. And NF, so NF increases as sigma A decreases. That means if the stress amplitude is less, then obviously the material will sustain for a longer number of cycles. Am I right? So if the NF is increases, the sigma A decreases, and vice versa, obviously. For the steel whose behavior there apparently exists as a stress amplitude, that there are two kind of SN curve you can see over there. That is purely depend on the material you use. The first one, okay, can you see the cursor right now?
Yes.
Yeah, this is the first one with a green line. In this, you can see one limit, the corresponding limit. So where the curve is getting flattened. Okay. So below this, if whatever the stress amplitude I can give, the material will sustain for a longer period. Okay, that's what it means. Okay. So this particular kind of SN curve will be there for the steel kind of material, okay, which exhibit a clear fatigue limit in the curve, which shows, okay, but some alloys like aluminum or some ductile alloys, very soft alloys, will not show that clear exhibit, will not show the fatigue limit as shown in the steel. What here it will happen? No? It will keep on decreasing. It won't have a limit. Okay, so if you get this kind of curve where I'm showing right now, which is a blue one, what is the information we can get from the curve is what is a fatigue life at stress S1. So if this is a stress S1, what is the corresponding fatigue life we can get out of it? Similarly, what is a fatigue strength for this particular number of cycle that we can get? The fatigue strength at N1 cycle. Then similarly, fatigue life at S1 cycle. This is the information we can get from the SN curve in this pattern, where it doesn't show a proper fatigue limit in the graph. Okay, fine. So this is called endurance or fatigue limit of the material. The fatigue limit is just about, as a thumb rule or in general, that will be 40% of the tensile strength of steel. When we do a fatigue testing at 0.1, like R is equal to -1, that means in a fully reversed condition, if we do a fatigue testing, then the fatigue limit of the material will be 40% of its tensile strength. So that's what I was discussed. I just said you before, after that only this word coming here. Okay. So this is another SN curve which shows very clearly what is the endurance limit and mild steel. This is how the results you get. And for the aluminum alloy, the curve will look like this. There is no fatigue limit. Instead of that, you will get a fatigue strength is specified for arbitrary number of cycles. That arbitrary number of cycles is nothing but 10 power 7 or 10 power 8. If the specimen is sustained for 10 power 7 cycles or 10 power 8 cycles, then that's it. So that is a very good stress level. That's a safe stress level to apply this specimen on. Okay. Fine. So let's go for the fatigue testing. The time just gone like that. Okay. So fatigue testing, there is ASTM standards in the fatigue testing, which is ASTM E466. So standard practice for conducting the force controlled constant amplitude axial fatigue test for metallic materials. I guess you can download this standard and you can read. So what does its standard says is how the test has to be done and how the specimen has to be designed and what is the dimension of the specimen should be there relatively. That's why I'm telling relatively in the sense the grip is, for example, I'm telling if the grip of the specimen is 4 centimeter, then the test section of the specimen should be 2 centimeter, like that. Relative dimensions is given in this ASTM E466 standard. Okay, so let's go to the fatigue testing machines and types. Okay, so in this fatigue testing, first apparatus, which is as I said before, Aula is a German scientist who developed a method to report the fatigue behavior of the material. So this is apparatus is used by him, and this apparatus is also named as Euler apparatus. So from the picture itself, you can clearly see that. So can you see my cursor? So this one is a specimen. Yeah, the S is nothing but the specimen. Okay, the two places there are two specimens are mounted, and the specimens one end is given to the spindle which is rotating. The other end they are applying a force with the help of a spring, maybe a load. Okay, so what exactly happening? The specimen is rotating at the same time. Cantilever bending is applied to the material. Can you see that? Can you understand the apparatus now?
Yeah.
Yes.
Yeah, I can.
Okay, so what is happening when the cantilever bending is applied to a material? The rotation is also taking place. So each and every part or each and every place of the material will experience both tension and compression. Am I right? So when that particular can example, so where the point A in the upper position of the specimen is experiencing the tensile load, and that same point A, if it comes down while rotating, it will experience the compressive load. Am I right? So what is happening here? We are subjecting the specimen to the maximum and minimum stresses equal in magnitude, opposite in sign. Did you get my point?
Yep.
Okay, so there is a rotating bending is happening, rotating bending fatigue is happening. So the stress ratio is obviously -1, and this is how the test works. So a pair of rotating test specimen is subjected to cantilever bending, and springs applied a constant force through a bearing, permitting the rotation of the specimen so that the bending moment varied linearly from the distance. If you can remember the cantilever beam shear force and bending moment diagram, you can appreciate this actually. So it is linearly varying right from the spring. Okay. Similarly, in such rotating bending test, any point on the specimen is subjected to sinusoidally varying stress as it rotates from tension top side of the beam to the compression bottom side of the beam, completing the one cycle, the 360 360-degree rotation. This happens. Okay, this is what I have explained before. I'm just telling it to you in a proper way, in words. Okay, again, this is also a rotating beam fatigue testing machine, but it's developed by R.R. Moore. So what is a invention or as a new thing he included is, in this case, he introduced a 4-point bending. It's not a cantilever bending, it's a 4-point bending. If you draw a free body diagram for this entire machine, you can get two upward forces in the roller support. I guess you can follow me. What is that? The laser pointer. Okay. So the two upward forces in the roller support is there, and two downward forces in this weight. These 2 points. Okay. So obviously that comes to there comes the 4-point bending beam. So what is a plus in 4-point bending beam? In this particular stress region, in this region, there won't be a shear stress. Okay, if you draw a shear stress diagram out of it, there won't be a shear stress, and the bending moment will be equally distributed in this region where the specimen is fixed. That's what is a unique advantage of this entire specimen. So this how the same thing is happening. The load is applied at the same time the specimen is rotated. All other things are same. There is no doubt in it. Okay. The two bearings near each end of the test specimen permit the load to apply while the specimen rotates, and two bearings outside provides the support. That's what I explained before. A hanging weight usually provides the constant force. There is no variation in it. And in this 4-point bending setup, a constant bending moment and a zero shear stress over the length of the specimen is experienced. Okay, that is unlike the previous experiment. That's how the RR more rotating beam fatigue testing is worked. Fine? To the bend?
Sim, tudo bem.
Okay, fine.
Okay. So this one is done by me. It's not done by R.R. Moore or Euler, but I didn't invent it, but I did it during my PhD. So what is happening here is you are not applying any rotation to the specimen. Here the specimen is a flat specimen. And in my case, I've done some surface modification so that I've kept the specimen over there and I applied only bending, a 4-point bending. You can see two supports. You can see two supports here and two supports upwards. So the bending applies like this. I guess you can follow this. Like this, the specimen is fluctuated so that the material fail exactly in this red circle. Okay, because there only the bending moment will be maximum and constant, and shear force was 0. So this particular area, the metal fails, and later I just analyzed it with a different way, and we have done it. This is 4-point bending fatigue test. Okay, so the next one, this is also done by me during my research PhD. So over here we have done tension fatigue. Okay, so it's a normal tensile testing. I could see one person in our group, Williamson. Am I right? So he was sitting in a place where I could see a tensile testing machine in his backdrop. Is he on the line? William. Okay, fine. And I saw a person sitting in the meeting with this kind of machine in his backdrop. Okay. Fine. So this is a normal UTS testing machine, like ultimate tensile strength testing machine, universal testing machine, what we say in India. So in this, we just mount the specimen in these two jaws. The specimens you can see in the bottom photograph. These are all the specimens prepared on the basis of ASTM E466 standard. Okay, so this one is mounted over there, and the constant fluctuating load is applied to the specimen, and one sort of time that will fail, and everything is noted down in the system which is placed here. And then photograph it is not shown, but this table, the system will be there. It is totally controlled, and the graph, everything will be generated in the system automatically. Okay, this is how right now is happening fatigue testing. Okay, and I will share this document. You can find these videos, which is really useful in order to visualize. I hope I've explained you in such a way that you can visualize what I'm telling. If you are not sure, if you need furthermore explanation, please go ahead and see these videos. You'll get more insight about fatigue testing. Okay, fine. So let's see what all the factors affect the fatigue life of the material. The first thing is surface roughness. Obviously, as I said before, we are keep on talking about the surface inhomogeneity, stress concentration, These are all the important things which will affect the material failure, like metal fatigue. Okay, surface roughness is nothing but you have to consider surface roughness as a small stress concentration in the surface. Okay, so if it is so, then definitely that particular area the stress will be maximum, the material will fail. That's it, as simple as it is. Okay, so that's how the surface roughness. And one fine example I can show here is what the same material with different surface finish, how the fatigue life differs. This one image is enough for you to understand the effect of surface roughness on the fatigue limit of the material. You can see that the same material, when it is lathe formed, its surface roughness is 105 micro inches. So micro inches. So the fatigue life will be 24,000. Okay. If I do a partly hand polishing, it will the surface roughness will drastically reduce to 6, and that will give me a 91,000 number of cycles in fatigue cycles. Similarly, the same material for hand polishing, it will give 1,37,000, and grounded and polishing, it's keep on increasing. It will keep on increasing. And at the same time, if it is super finish, it will be 2,12,000 cycles. It will give, like means 212,000 cycles. So this how, like this only the surface roughness will influence the fatigue life of the material. Okay. Not only the surface roughness, I hope you would have come across the terms called carburizing, nitriding, and many things which changes the property of the surface like hardness and other things. So those processes will also increase the fatigue life of the material. That's what the effect of surface properties having. Yeah. And the third one, the very important thing is surface residual stresses. I guess many of you would have come across this term residual stresses, and the stresses which remain even after the process stop, that is called residual stresses. That remain in the specimen is called residual stresses. So this residual stresses could be a positive, could be a negative also in both the way. Like if it is positive, then it is a tensile residual stresses. Am I right? So if it is a tensile residual stress, it is negative for the fatigue behavior. And if it is a compressive residual stress, it is a positive for the fatigue behavior. I hope I'm not confusing you. Okay, so if it is a tensile residual stresses, when a material is supplied to a service load, the tensile residual stress present in the material will get superimposed on the applied stress. Then what will happen? The material will fail very quickly. The early crack nucleation will happen and early failure you can experience. At the same time, if we have a compressive residual stress in the surface, what will happen? If we superimpose a compressive residual stress on the surface service load, then there will be a reduction in the stress and you will get a prolonged life. That's all. As simple as it is. Okay, that's how the surface residual stress influence the fatigue life of the material. And this one fine example, you can see how effective the surface residual stress is. Okay, so here the nickel chromium alloy, which is notched and short peen and polished and smooth. A dot, can you see the laser pointer right now?
Yes, you can.
Okay, this notched specimen have a very low fatigue life. Okay, but at the same time, if the notched specimen is subjected to a short pinning is nothing but a process of imparting the residual stress, compressive residual stress in the material. Okay, then you can tell in that way. If the notched specimen is having a compressive residual stress, then that specimen is behaving as like a polished specimen without notch. Okay, so that's what this entire graph shows you. Then what is the takeaway from this graph? So a notch effect can be remedied or can be compensated by inducing the compressive residual stress in the surface. So how much important it is, just imagine. Okay, even a notch effect can be eliminated. Okay, so that's how the surface residual stress is important. And similarly, the mean stress about which the fluctuating load is taking place. Okay, that's called a mean stress. So that also have a very important effect in the fatigue life. So the mean stress will also affect the fatigue life. This influence is represented here. Okay, so if we go more on the mean stress, for example, what is mean stress? About which the cyclic load is imposed. Okay, if I go more into the tensile region, That means positive stress. I am taking the material to 200 MPa. I am stressing the material. Pulling the material to 200 MPa. After that, I am implying like imposing the cyclic load on it. Okay, so from 200 it is going up and down. So what will happen? Definitely, if you increase the mean load, mean stress, then the fatigue limit will go down. The fatigue behavior of the material will come down. Okay, so that's how the main stress is related to the material. You can see in the graph. So if sigma 3 is greater, then it will have a very less fatigue life. Sigma 2 is the higher the mean stress, lower the fatigue life. That's it, as simple as it is. So I have a couple of slides right now, maybe another 4 or 5 slides. So can I complete it or we'll finish it? It's 5 o'clock right now. Hello.
Yes, Sudaraga, go ahead.
Okay, can I complete it? Fine. Thank you. Okay, so right now we understood what is fatigue and what is the importance of fatigue and how does the fatigue crack initiates, grow, fracture, everything, and then how the fatigue is tested, how we can quantify, how we can present that fatigue results, everything we have seen. Right now, how we are going to post-mortem the fatigue failure, that we are going to see right now. What is post-mortem? How we are going to analyze the fatigue from the microstructural features of fatigue. What are all the things will be there in the fracture specimen, and what does it tell to you? What does the information you can absorb from that? That's all we are going to see right now. So it is fatigue fractography. Okay, or as sorry, I couldn't pronounce this Portugal in any way. So this fine photograph, you can see a very clear position where the crack originates and it grows in this way, and then this growing area is nothing but the fatigue zone, and this one is final fracture where you cannot see any traces of growth. It's kind of brittle failure over here, or you can say it is an overload failure. Okay, this is one fine example. Let me see. Let me explain you in deeper manner. Okay, so first feature which we are going to see right now is calm shell or beach marking in a fatigue failure specimen. Okay, so it represents that the portion of the fracture surface over which crack progression was gradual. Okay, so over in the entire region, if there is a region with lot of calm shell marking, then that region is nothing but a gradual slow growth region. Okay, so the rough fibrous area of the remaining portion of the fracture surface corresponds to the final fracture. That's what we have seen in the previous slide. Okay, so remaining area of the fractography is nothing but the final fracture. So the relative areas of the slow and fast fracture regions are a rough measure of magnitude of the maximum cyclic stress and the material fracture toughness and tensile strength, everything. Okay, so this relative region, how far the material is resisting the crack, we can get from it. And if the crack growth region is very small, then the material is obviously said to be a brittle failure. Okay, if that is really large, then the material is said to be a ductile failure. Okay, so from this information itself, we can have a very rough calculation or very interpret the nature of the material. That's what I'm trying to say. Okay, so this is another image where you can see the calm shell marking at the very top corner. Okay, the distance between the ring markings or calm shell markings are macroscopically visible. Okay, so you can just with the naked eyes you can see. You not to have any microscope or anything to see the calm shell marking. Just please be very careful in the terms. Calm shell marking alone with naked eyes you can see. Okay, it is not a measurement of crack advance per stress or strain cycle. Okay, it's not for each and every stress cycle what it goes. That is different. That we will come to later part. Okay, but this is if, for example, let me tell you in a very practical scenario. You have a machine. Okay, in that machine there is a component which is undergoing a fatigue failure. Okay, that means a crack is growing in the machine component. You are operating the machine in the night, like 5 o'clock in the evening, maybe 10 to morning 5 o'clock. You are operating the machine. Okay, and then you are stopping the machine. And the next day you're coming, the same timing, you are just operating the machine. So what is happening? The crack will grow and stop. The crack will grow and stop. Okay. So that marking is nothing but a Kamshan marking. Okay. So for example, the similar kind of marking you can see in the trees. Okay. When you cut the trees, you can see several rings in it. So based on that rings, they would have people will judge its age. Okay. Similar to that. Okay. So this is, here comes the striations. Striations just opposite to that. So here fatigue failure typically occurs over many thousands of or sometimes millions of load cycles. For each and every load cycle, the crack will advance practically. Am I right? So for each and every load cycle, the crack will advance. If the crack is advancing, it will leave a footprint or it will leave an impression for each and every cycle. So that impression is nothing but the striations. Okay, so slowly crack advances only microscopic distance per cycle. That is very important. So this feature you cannot see in the naked eyes. Microscopic distance advanced by a crack per cyclic load or strain, cyclic strain, and forms a ring marking. This also kind of ring marking only, but it's very, very closely packed and it's a microstructural feature. It's like microscopical feature. Okay, visible under high magnification called striation. This is how it looks. Okay, the previous images are all are normal photographs, but this one is my electron photograph, like SEM. Okay, so the striation spacing in the laboratory will have equally spaced. Then generally it was equally spaced because you are applying a constant amplitude. Obviously, it should be equally spaced. But that means in laboratory failed specimen, it may look very, very good, very beautiful. But in normal failure, it won't look like that. Okay. But in engineering structure, fatigue striations varies due to variable stress loading. Okay. Striations and Kamshal markings are not the features of fatigue caused failure alone. That is another important thing you have to note. They also caused by stress corrosion cracking, hydrogen embrittlement, everything. Okay. The striation spacing denotes the slow crack advance. And so if the crack advances rate is relatively large, if the material is very, have very less resistant or the crack is advancing very fast, then there won't be any striations. Okay. So in such cases, the large cracks will be interlinked and ductile failure may kind. Okay. And this is another image from my research I did. So this is a fracture, like fractography analysis of the fatigue failed specimen. It is a tensile fatigue, and two sides are laser beamed. So in this laser beam is nothing but the process of imparting the compressive residual stress in the near surface region. Okay, so in this region, the crack doesn't initiate, but the side where the compressive residual stress is not there, the crack initiates. So you can see that. So from there, the crack propagates, and these are all the fracture area, the final fracture area. This one is fatigue zone. Okay, so you can see the striations in this region. Okay, this is the striations which I observed during my PhD. And this is this is a cylindrical specimen, so it's a circular cross section. So here you can find the crack initiation in this subsurface region, okay, because the surface is having a compressive residual stress due to the shock beating. So here the crack initiates and it grows. So this how here the crack initiates in the surface. So the lines which is going away from the crack initiation site is nothing but the river lines, what we call in the fatigue analysis. Okay, if you track back the river lines and if you come to a point where it converges or joins together, that point is nothing but the initiation point. In all these three photographs, you can do that. You can trace back the river lines. Here also, you can trace back from here. You'll come to an initiation point. Here also the same way. Here also the same way. Everything. Okay. Thank you. Thanks for your patience. I took 10 minutes extra. So this is how the fatigue is explained, and this is how the fatigue is tested, and this is how the fatigue is analyzed.
It's okay, thank you. Are you going to share this presentation with us?
Yeah, I'm going to share it. Yes, definitely. How many of them are there? Yeah, it's the time for frequency. Someone has asked question. I'm really sorry. Just now only I noted the came to the normal screen. Yeah, frequency usually we do in 15 to 20 hertz. 20 hertz is nothing but 20 cycles per second. Okay, so I did it in 15 hertz to 20 hertz. It depends on the material, like the capacity of the machine, and you can go up to 200 hertz. There is no problem at all. That doesn't affect your result. Okay, as per the literature. Okay, Rafael. Okay, Mr. Lucas, did I answer your question?
No, okay.
Yeah. Please tell me, please ask your doubts if you have anything, and that'll be,
Tudo ok.
yeah. Please let me know if you have any suggestions to improve. You can find my number in the group. Let me share it once again. You can message me in that. Okay, I'll share you once again. If you have any doubt on what I taught, you can talk to me in WhatsApp, and you can talk in Portuguese also. While writing, it's no problem because I can cut, copy, paste, and I can understand what you're telling. And okay, so only while speaking, I have a problem in Portuguese, but soon I will learn it. Yeah, I'm in the process of learning it. Any doubts?
No, it's okay.
It's okay.
Teacher, is possible to provide us this material by email or something else, please?
Yeah, I'll just make it as a PDF, and I will share to Professor Anna, and Professor Anna could share you in the group, or I'll just ask. Definitely, I will share this material for sure. Okay, and I personally suggest some good books. Yeah, book by
Thanks.
professor. It'll be very simple. It'll be very easy to understand. Callister, and then Courtney. It'll be more deep. You can understand the science in it. Courtney, you can understand. It's really good book. And Dieter is furthermore good book. Okay, so Dieter, Courtney, and then Callister. These three books you can refer for this topic.
Good.
Yeah.
Yeah. Was the group created? I am not yet. Okay, you have a Google Classroom. Okay, fine. Then I will share the data, like the PPT with the professor, so professor can share it.
Yes, we have the group, but it's not being used actually. Nothing's posted there. So if you can also tell Professor Ana Paula to post all the slides there, not only from your class, but the previous one, would be great for us to save and check it later.
Okay, for the other classes also. Okay, sure.
Thank you.
Thank you. Thank you. Do you need any? Is everything clear?
For me, ok.
Yes.
Yeah.
Então,
Yeah. So the session is open for questions. If you have any questions, please go ahead and ask. I'm here to answer. Okay. So if you don't have questions, we will end up the session. And at the same time, if you have questions, when you go through my slides also, please message me or mail me, whatever it is. I'm happy to assist you. Okay. Thank you. Thanks a lot for being patient. It's been a great experience to present my experience to you. Thank you. See you then. Ciao.
Thank you very much.
Ciao.
See you later.
Bye-bye.
Ciao, ciao.
Thank you.